Welcome. This is part 2 of the lecture on reduced row echelon form. So what we would like to do is to apply these row operations to an augmented matrix. So given a linear system of equations, we form the augmented matrix corresponding to that system, and we apply row operations, and that will lead us to the solution set of the system. So the row operations are swapping rows, multiplying a row by a non-zero scalar. Scalar is another word for a number. And then the third type of operation is a combination of multiplying a row by a scalar, by a non-zero quantity, and adding that to another row and then replacing. Okay, so here multiply row I by the number alpha, add that to row j, and then replace row j. So these are the three types of operations, row operations, that we are going to apply to an augmented matrix. So to follow this illustration, let's see. So we consider this system with three equations, three variables. The augmented matrix of this system is going to contain the matrix of coefficients together with the vector of constants. So it will be a 3 by 4. This matrix here, this augmented matrix, is a matrix that is 3 by 4. 3 rows, 4 columns. And so what we do first is that we apply this operation that says we're going to multiply row 1 by -1 and add that to row 2. Okay, multiply row 1 by -1. Excuse me. By doing that, we get -1, -2, -2, and -4. And if we add these numbers to the second row here, okay, so we have -1 plus 1, that gives us 0, -2 plus 3, that gives 1, -2 plus 3 gives another 1, and -4 plus 5 gives another 1. So multiply row 1 by -1, add that to row 2, and then substitute, replace the second row. So that second row is substituted by the new row we'll obtain by doing this operation, and the comparison is now this is a matrix, row equivalent to the original augmented matrix, such that we have created a 0 on one of its entries. Okay, and okay, so we continue. Now multiply row 1 by -2 and add that to row 3. We're do this operation to this previous matrix, and that is something that will give us a 0 on this entry here. Okay, so this matrix is now row equivalent to the previous one, which is in turn row equivalent to the original augmented matrix. And then what we do next is multiply row 2 by -2 and add that to row 3. And by doing so, we end up with this matrix that now has a 0 on this entry, on this position. Okay, so and the next operation is multiply row 3 by -1, and then we obtain this. What you can see is that this matrix here has some structure. This structure is such that this is providing a little bit of a structure. There are some of these entries that are 0, and there is some triangular shape in this structure. And what we can read from here is something that we had previously discussed. But let's see what else. So the matrix in this form is row equivalent to the augmented matrix, the original augmented matrix of the system of equations, and they have the same solution. Okay, they have the same solution set as the original system of equations. So this would be the augmented matrix that is associated. This augmented matrix is associated with this system here, and that system has the same solution set as the original system. Now, there is a definition of saying that a matrix is in reduced row echelon form means that the matrix is going to satisfy all these conditions. There is a row, basically, if there is a row of zeros, this row has to be located at the bottom, below the bottom part of the matrix. The leftmost non-zero entry of a row is equal to 1. Okay, so these entries on a given row, that the first non-zero entry is going to be a 1, and that is going to be located in the leftmost part of a row, and those ones are going to have a special name. They're going to be called pivots, and they're going to be used to denote the columns, the so-called pivot columns. Okay, but the other condition is that the leftmost non-zero entry of a row is the only non-zero entry of its columns in that column. Okay, and if we consider any two different leftmost non-zero entries, one located in row I, column J, and the other one located in row S, column T, then, well, you can read this, but I'll give you a few seconds for you to process this, and then this type of thing, when you read it, seems a little mathy and complex, but is in practice is nothing to worry about. Okay, let me say something more about the leading ones. The leading ones are those leftmost non-zero entries in a given row. They're also called pivots. Okay, so the number of non-zero rows will be denoted by R, and those that number of non-zero rows is precisely the number of these leading ones in the matrix. A column containing a leading one will be called a pivot column, and here comes some notation that is going to be very important throughout, well, for a long time. The R, the little r, denotes the number of non-zero rows. And we are going to define a set containing indices. And D1, D2, D3, these will be indices. Okay, and there are as many elements in this set as non-zero rows in the matrix, in the so-called reduced row echelon form matrix. Okay, so there is D1, D2, D3, all the way to D sub R. These are simply indices of the matrices corresponding, the indices in the matrix corresponding to pivot columns. They are stored here, listed here in order, such that the first one is the smallest, the last one is the largest, and they are also ordered in between. And then there will be another set called capital F. So capital D store indices of pivot columns, and then capital F stores the rest, all the other indices. Okay. Again, this will become clearer once we start working this, and you're going to do a lot of practice. So the principal feature of the row echelon form is a padding of leading ones. Okay, and let's see. So with those definitions in mind, let's try to answer this question. Is this matrix here in reduced row echelon form? Well, you can notice that all entries, that all rows that are rows of zeros are located in the bottom part of this matrix, right? So here at the bottom, there are 2 rows of zeros, okay? And then it's also common to write the leading ones with this notation that is like enclosed by a rectangle or something like that. So they are denoting leading ones. So in the first row, there is nothing to the left of this one. So on the second row, everything that's to the left of this one, every entry to the left of that one is 0. Okay. So that one is indeed the leftmost non-zero entry of row number 2, and so is the next one. Okay. So in this case, we would say that the number of leading ones is 3. So R equals 3, and the indices of columns that are called pivot columns, columns containing leading ones, are column number 1, column number 5, and column number 6. So the indices of columns that are considered pivot columns are 1, 5, and 6. So that set capital D contains 1, 5, and 6. This matrix, okay, this matrix has, let's see, this matrix has 2, 4, 6, 8 columns. Okay, so this matrix has a total of 8 columns. So that means that the set capital F is going to store all the other numbers that are not 1, not 5, and not 6. And so F contains 2, 3, 4, 7, and 8. So the definition of these two sets, this is how it goes. Once you are assured that you're positive that the matrix is in reduced row echelon form, then you start first you determine what is the number of non-zero rows, and then you immediately determine what are the indices stored in the set capital D and what are the indices stored in the set capital F. Now, is this matrix in reduced row echelon form? So this will also be another acronym. So reduced row echelon form. So that will be very common acronym. RREF denotes reduced row echelon form. So is this matrix in RREF? And the question is, well, is this matrix is not in RREF. Why is that? Well, it turns out that here this row is a row of zeros, and that row of zeros would need to be swapped, would need to be moved farther down this matrix. The definition of RREF, this may be close to being RREF, but it's not quite, because the definition says that all rows of zeros will be located at the bottom part of the matrix, and that is not satisfied here.